Hi, everyone. We're Team NAU Capstone, and we're representing Northern Arizona University for the New Mexico State University District use case. Okay, our team is comprised of 4 senior mechanical engineering students and our token electrical engineer, Jack Viola. I, Corey Burke, am the project manager. Elizabeth Griffith is in charge of our finances. Grant Hale was in charge of standards and regulations. Daniel McConnell was in charge of logistics and Aurora Solar, and Jack Viola was in charge of battery management and OpenDSS. Okay, the team's approach to the competition was to first generate the most amount of energy possible while staying financially viable. And then our secondary objectives were to minimize losses and to have innovative ideas. Our team met once every week with our faculty advisor, Dr. David Trevis, and we also met with a business professional, Christine Kettle. Okay, the system design is made up of 3 subsystems: the geothermal substation ground mount system, which is located in the dirt lot east of campus, the Pan American Center parking awning, which is south of the Pan American Center, and then our Hadley Hall Spanish solar tiles system with a 220 kilowatt battery storage system. Okay, for the geothermal substation, it's 3 miles east of campus, so it won't be obstructed by anything, won't obstruct anything on campus, no shading there. The ground mount system has a 30-degree tilt, which we found was optimal for manufacturing. And we use SunPower T5 SPR 310 monocrystalline silicone panels with 3 extremely efficient inverters with a maximum AC power of 880 kilowatts.
So the next design is the Pan American Center solar parking awnings, and these are located in the parking lot as shown in the previous slide, and they will shade a total of 577 parking spaces. The team proposes that these permits for shaded parking will cost $78 more each year, and this extra charge for shaded parking will potentially provide an extra $1.1 million of revenue to help pay off the initial installation costs. The same SunPower solar panels and SMA America inverters from the last design will be used for this design, but this time it will only require 2 inverters. For the next design, we chose to design a solar tile rooftop system on Hadley Hall using HON tiles as the PV modules. These HON tiles are a new technology providing an innovative renewable energy visual on Hadley Hall. They're aesthetically pleasing, making them a great way to showcase the university's push towards renewable energy. Along with the PV systems, the team designed and implemented a battery storage system. For the system, saltwater batteries were chosen, and after optimization, the size of the system was decided to have 580 kilowatt hours of capacity. The saltwater batteries were chosen because they are easily and 100% recyclable, and they have a wide charge and discharge range, and they're very low risk, especially with fire. The team found that the Green Rock saltwater batteries would work perfect for the system because they come pre-packaged and optimized in a storage container from the manufacturer. This reduces the construction and electrical costs for implementation. The battery storage system will be tied to the grid, but have the capability to provide energy to critical systems during a grid outage. With all the designs completed, the team was able to estimate how the proposed system would operate. In the figure, you can clearly see in red when the PV system is serving the load, and it's a bit harder to see, but in blue, you can see where the battery is charging and discharging, I'm sorry. And the battery, both the PV system and batteries will serve to lower peak shaving, and they work to keep the critical systems on. Yeah, thank you for the next slide. The proposed system is expected to offset a total of 31% of the total consumption and can be expanded upon whenever desired. The team suggests that the system is expanded when battery storage is a bit cheaper so the university can save more money by going green. It is expected that battery storage costs will be reduced by 21 to 67% by the year 2030. If this cost is reduced by the average of these two values, 44%, a larger battery storage system could be implemented, saving the university even more money and moving towards their goal of carbon neutrality by 2050. Increasing the system size would also benefit the university because they would be able to sustain more critical systems during grid outages. And if they want to meet that goal of carbon neutrality, battery storage would be a great asset to have because renewable energy is inconsistent and the battery storage can help mitigate that inconsistency. With our proposed design, the university's critical load of 16% is expected to be sustained 31% of every potential 2-hour grid outage throughout the year.
So I'm just going to talk you guys through some of our OpenDSS modeling and just operation of our simulated models. We used OpenDSS mainly to perform loss and fault analyses, as well as observe phase matching, kilovolt mismatches, and service drops, and really just to verify all the work the mechanical team did in Aurora Solar and the other simulation programs. A lot of this is going to be a review from other systems because we were working off the new NMSU base system. So I'm just going to highlight some key stuff about our design specifically. In the upper right, you can see a plot of the per unit voltage as the distance from the main service node increases. Originally, when we received our OpenDSS model of the campus before we modified it at all, the slope of this line was negative, where it was a much higher per unit closer to the node and then sort of dropped off the further you got. But after adding these PV systems to closer to the service drops, it really boosted the per unit further down the line. And I think the reason that it's a little bit lower closer to the node is that this is where our largest system is at the dirt lot, and also where our only battery subsystem is. So there are some just impedance mismatches still existing within the system because I was working sort of for like right down to the 11th hour in this, and phase matching is something that can be pretty easily done with our inverters. They have load capacitor or compensation capacitor ports so that you can analyze the system in real time to see what sort of phase mismatches exist and where, and then you can compensate for those by adding capacitors at the inverters. Those horizontal red lines on the same graphic are sort of the bounds of the original system's per unit voltage. And so this just kind of verifies that we stayed within that range. And in the middle, you can see the daisy plot of the circuit. And one sort of key thing to notice here is that the dirt lot system is sort of branching up off the top in a sort of like angle, like a V. And this is just because OpenDSS, I couldn't just sort of plug it into the closest place on a line because the lines are really just node connections and you can only interact at a node. So that was sort of the closest node I thought to the system that would work best for our modeling. But if this system were to be actually implemented, this would probably just be attached directly into the grid line that's coming off from the service station. And yeah, our real main goal with the OpenDSS design was to implement our subsystems in a really non-invasive way so that we're not making any huge industrial changes to the base system. Because if we're replacing all the service lines and all of this, that's just a lot of extra costs that'll add up very quickly. So our main goal was to just sort of have this be a fit in place, connect it where it needs to go, and it won't be disrupting anything in the system. And on my next slide, I'm going to talk to you quickly about some system operations. There are two main controller types within our system. These are the battery controllers that Daniel was talking about. that come pre-packaged, built into the Green Rock battery modules. And the other controllers are the inverter microcontrollers. And just, I'm going to talk a little bit more about the saltwater batteries, just because this is a really emerging technology. It's pretty new, but doing the research on it, it is extremely well geared for solar and PV applications. A lot of places are claiming that their batteries have 100% battery depth of discharge, which means that they could charge it up to 100% and then discharge it down to 0%. However, I did not include that figure in our models. I used a 95% depth of discharge rate because looking more closely at the research, obviously the chemical reaction is completely reversible in these batteries, but the 100% depth of discharge is a little bit optimistic still, whereas 95% is a lot safer for actual application purposes for our modeling. Also, a lot of these batteries, Green Rock included, are cradle to cradle environmentally safe certified. This means that when they're being produced, being used, and being recycled, all the processes and materials that go into making them and producing them are basically like not carbon neutral, but they're not dealing with a lot of these chemicals that traditional batteries are handling that are a lot harder to recycle and do a lot of damage to environmental areas that they are placed as waste. Talking a bit about the integrated controller in those batteries, we use these controllers to implement our peak shaving that Daniel discussed, as well as discharge rate regulation and power factor correction. The controller within the battery module is capable of doing some power factor correction. However, we don't want to stress these batteries, so we did not set the power factor target to 1, which would be 100% real power being delivered, just because we want to extend the lifetime of these subsystems as long as possible, because a big part of the cost is going to be the turnover of batteries. But yeah, the maximum power point tracking of the inverters and the discharge rate regulation are meant to sort of keep everything working well. And then the peak shaving and power factor corrections, or mostly the peak shaving, is really geared just towards saving the university money on their power bill and supplementing the grid service. And next, I'm going to hand off the presentation to Grant Hale to talk about our financial model.
Our team has come up with a PPA price of 2.3 cents per kilowatt hour, while Paso Electric has charges the university 1 cent per kilowatt hour, both in AC. We're using a battery stacking system design that creates backup power for potential power outages and that the university may encounter. On the right side, you'll see the internal rate of return, net present value, and customer net present value. As you can see, our customer net present value is sitting at approximately $6 million. The university's estimated carbon offset value is 2.8 cents per kilowatt, and our photovoltaic systems will create enough energy to meet the customer net present value over the 20-year time period, making the project financially viable. Using the UDC zoning and Las Cruces parcel maps, we determined that the geothermal substation ground mount system falls under the Dona Ana County jurisdiction, and the university lies under the state's jurisdiction. The southwest corner of New Mexico State provides the most suitable geography for photovoltaic systems in the state. The Spanish-style hon tiles being placed on Hadley Hall and the Pan American Center solar parking are the most attractive designs. They showcase the university's care for the environment to the faculty, students, and community, giving New Mexico State University a tremendous PR boost. All of our proposed designs comply with the university's district master plan and strive towards a 2050 carbon neutrality goal that New Mexico State University has committed to. As for other land uses, our team has determined that the greater area of Las Cruces, New Mexico does not inhibit any critical habitat for threatened or endangered species. The state of New Mexico has adopted the 2015 International Building, Residential, and Fire Codes. Using these standards, our team developed potential construction plans for each battery and photovoltaic system individually. These plans meet all standards and codes for the 2015 IBC, IRC, and IFC that are applicable. These construction plans will then be submitted to the appropriate officials and approved to acquire the necessary construction permits. Once these permits are acquired, construction may begin and will take approximately 6 months. The team will engage the decision makers by identifying what motivates them, communicating progress, and being consistent. Once all permits have been acquired, the team has integrated all codes into the design, which will ensure successful deployment.
With that, we'd love to hear you guys' questions for us.
Perfect timing.